Dear students, welcome to today's lesson on acceleration due to gravity. It was Galileo who recognized that all bodies, irrespective of their masses, are accelerated towards the earth with a constant acceleration. Galileo said that all objects fall with the same acceleration unless air resistance or some other force acts on them. Today, we will discuss about the acceleration due to gravity in detail. Earth attracts every other body lying near or on its surface towards its center. The term gravity is used for the force of attraction exerted by the earth on the body. Therefore, a body under the effect of gravitational pull must accelerate. The acceleration produced in the motion of a body under the effect of gravity is called acceleration due to gravity. It is denoted by small g. Newton made a statement that the acceleration of an object falling toward the earth should vary as 1 upon re square, where re is the radius of earth. However, acceleration due to gravity near earth's surface is constant.
Let us see an observation. Suppose we have a unit mass lying at a distance r from the center of the earth somewhere in space. If we plot a graph between the gravitational pull F exerted on the unit mass and variation of its separation r from the center of the earth, we get an exponential graph, value of gravitational pull at the surface of earth, that is at r equal to re, is found to be 9.8 Newton. Since this force is exerted on a unit mass, hence the value of acceleration due to gravity at the earth's surface is 9.8 meter per second square.
Acceleration due to gravity ਨੂੰ ਨਾਪਣ ਲਈ ਅਸੀਂ ਅਰਥ ਨੂੰ ਇੱਕੋ ਜਿਹੀ ਡੈਂਸਿਟੀ ਵਾਲੀ ਸੋਲਿਡ ਸਫੀਅਰ ਮੰਨਦੇ ਹਾਂ। ਅਰਥ ਨੂੰ ਬਹੁਤ ਗਿਣਤੀ ਦੇ ਵਿੱਚ ਸਮਕੇਂਦਰੀ ਸਫੈਰਿਕ ਸ਼ੈਲਸ ਵਾਲਾ ਵੱਡਾ ਸਫੀਅਰ ਮੰਨਿਆ ਜਾ ਸਕਦਾ ਹੈ, ਜਿਸ ਦੇ ਕੇਂਦਰ ਵਿੱਚ ਛੋਟਾ ਅਤੇ ਤਲ ਤੇ ਵੱਡਾ ਸਫੀਅਰ ਸੈੱਲ ਹੈ। ਅਰਥ ਤੋਂ ਬਾਹਰਲਾ ਪੁਆਇੰਟ ਨਿਸ਼ਚੈ ਹੀ ਸਾਰੇ ਸੈੱਲਾਂ ਤੋਂ ਬਾਹਰ ਹੋਵੇਗਾ। ਇਸ ਲਈ ਸਾਰੇ ਸੈੱਲ ਬਾਹਰੀ ਪੁਆਇੰਟ ਤੇ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਲਗਾਉਂਦੇ ਹਨ, ਜਿਵੇਂ ਉਹਨਾਂ ਦਾ ਮਾਸ ਸਾਂਝੇ ਕੇਂਦਰ ਤੇ ਕੇਂਦਰਿਤ ਹੋਵੇ। ਸਾਰੇ ਸੈੱਲਾਂ ਦਾ ਇਕੱਠਾ ਮਾਸ ਹੀ ਅਰਥ ਦਾ ਮਾਸ ਹੈ। ਇਸ ਲਈ ਅਰਥ ਦੇ ਬਾਹਰੀ ਬਿੰਦੂ ਤੇ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਇਸ ਤਰ੍ਹਾਂ ਹੈ ਜਿਵੇਂ ਅਰਥ ਦਾ ਸਾਰਾ ਮਾਸ ਇਸ ਦੇ ਕੇਂਦਰ ਤੇ ਕੇਂਦਰਿਤ ਹੋਵੇ। ਇਸ ਦੇ ਕੇਂਦਰ ਤੇ ਮਾਸ ਦੇ ਸਥਾਨ ਪਰਿਵਰਤਨ ਨੂੰ ਕਈ ਫਿਜ਼ੀਕਲ ਸਿਸਟਮਾਂ ਤੇ ਲਾਗੂ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। ਉਦਾਹਰਣ ਵਜੋਂ ਨਿਸ਼ਚਿਤ ਆਕਾਰ ਦੇ ਦੋ ਏਰੀਆਜ਼ ਵਿੱਚ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਓਨਾ ਹੀ ਹੋਵੇਗਾ ਜੇ ਦੋਵਾਂ ਦਾ ਸਮਾਲ ਮਾਸ ਪੁਨਰ ਸਥਾਪਿਤ ਹੋ ਜਾਵੇ। ਇਸ ਲਈ ਅਰਥ ਦੇ ਤਲ ਤੇ ਕਿਸੇ ਬੋਡੀ ਦਾ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਹੈ F ਬਰਾਬਰ G ਇੰਟੂ ਅਰਥ ਦਾ ਮਾਸ ਇੰਟੂ ਬੋਡੀ ਦਾ ਮਾਸ upon square of the distance between them. ਇੱਥੇ me ਅਤੇ m ਅਰਥ ਅਤੇ ਬੋਡੀ ਦੇ ਮਾਸ ਨੂੰ ਦੱਸਦੇ ਹਨ। ਅਰਥ ਦੀ ਗ੍ਰੈਵਿਟੀ ਕਰਕੇ ਕਿਸੇ ਮਾਸ ਦੇ ਐਕਸਲਰੇਸ਼ਨ ਨੂੰ ਚਿੰਨ੍ਹ ਸਮਾਲ g ਨਾਲ ਲਿਖਿਆ ਜਾਂਦਾ ਹੈ, ਜੋ ਨਿਊਟਨ ਦੀ ਗਤੀ ਦੇ ਸੈਕੰਡ ਲਾਅ ਨਾਲ ਸੰਬੰਧਿਤ ਹੈ, ਜਿਵੇਂ F ਇਕੁਅਲ ਹੈ mg। ਦੋਵਾਂ ਦੀ ਤੁਲਨਾ ਕਰਕੇ ਸਾਨੂੰ ਮਿਲਦਾ ਹੈ mg equal to capital G into me into m upon re square. So, अर्थ दे तल ते एक्सेलरेशन ड्यू टू ग्रेविटी होवेगी g equal capital G into me upon re square. Here you can notice a special characteristic of gravitational acceleration, that the gravitational acceleration g does not depend on the mass of the body on which the gravitational force is acting.
Acceleration due to gravity body ਦੇ mass ਤੇ depend ਨਹੀਂ ਕਰਦੀ। ਭਾਵ acceleration due to gravity ਡਿੱਗ ਰਹੀ ਵਸਤੂ ਦੇ ਬਾਰੇ ਜਾਂ ਹਲਕੇ ਹੋਣ ਤੇ depend ਨਹੀਂ ਕਰਦੀ। ਇਸ ਲਈ ਇਹ ਕੋਈ ਫਰਕ ਨਹੀਂ ਪੈਂਦਾ ਕਿ body ਭਾਰੀ ਹੈ ਜਾਂ ਹਲਕੀ।
Knowing the mass of Earth, which is 5.97 into 10 raised to the power 24 kilogram, the radius of Earth, which is 6.37 into 10 raised to the power 6 meter, and the value of capital G. The value of small g can be calculated as g equal to 9.81 meter per second square. The measured value of acceleration due to gravity depends on the point of measurement in vertical direction with respect to the mean surface level. To discuss the effect of the vertical position of the point of measurement, we consider the Earth as a perfect sphere of radius re and uniform density. Acceleration due to gravity at a height or altitude. Gravitational acceleration due to Earth on its surface is equal to gravitational force per unit mass and is given by small g equal to capital G into me upon re square. It is clear that acceleration due to gravity will decrease if measured at a height h from the Earth's surface. Mass of the Earth remains constant, but the linear distance between the object and the center of the Earth increases. The net result is that the gravitational acceleration decreases due to a value small g dash as given by the equation g dash equal to capital G into me upon r square. Since this point is outside the Earth, its distance from the center of the Earth, that is r, is equal to re plus h. Hence, the relation for small g becomes g dash equal to capital G into me upon the square of re plus h. We know that at the surface of the Earth, g is equal to capital G me upon re square. On dividing the value of g dash by small g, we get g dash upon g equal to capital G into me upon the square of re plus h upon g into me upon re square. On simplifying this equation, we get g dash upon g equal to re square upon the square of re plus h. That is, g dash upon g is equal to 1 upon square of 1 plus h by re. Hence, we have g dash equal to g into 1 plus h by re whole raised to the power minus 2. This relation represents the effect of height on gravitational acceleration. We can approximate the expression for the situation where h is very much smaller than re. By using binomial expansion, the expression for g dash becomes g dash equal to small g into 1 minus 2h upon re plus higher powers of h upon re. as h is very much smaller than re, we can neglect the higher powers of h by re in the binomial expansion, and g dash becomes approximately equal to g into 1 minus 2h upon re. It follows that as we go up, the value of acceleration due to gravity decreases. We should always keep in mind that this simplified expression holds only for the condition h very smaller than re. For small vertical altitude, acceleration due to gravity decreases linearly with the slope of minus 2 by re. ਜੇ ਹਾਈਟ ਜ਼ਿਆਦਾ ਹੋਵੇ ਜਿਵੇਂ ਸੈਟੇਲਾਈਟ ਦੇ ਸੰਬੰਧ ਵਿੱਚ ਤਾਂ ओरिजिनल एक्सप्रेशन g dash equal to capital G into me upon re plus h the square, जहाँ g dash is equal to g upon 1 plus h upon re the square. ਹੁਣ ਅਸੀਂ ਗੁਰੂਤਾ ਬਲ ਕਰਕੇ ਐਕਸਲਰੇਸ਼ਨ ਉੱਪਰ ਹਾਈਟ ਦੇ ਪ੍ਰਭਾਵ ਦਾ ਗ੍ਰਾਫ ਵੇਖਦੇ ਹਾਂ।
ਮੰਨ ਲਵੋ ਇੱਕ ਰਾਕੇਟ ਅਰਥ ਤੋਂ ਦੂਰ ਜਾ ਰਿਹਾ ਹੈ। ਰਾਕੇਟ ਦੇ ਅੰਦਰ ਭਾਰ ਤੋਲਣ ਵਾਲੀ ਮਸ਼ੀਨ ਤੇ ਇੱਕ ਇਕਾਈ ਮਾਸ ਵਾਲੀ ਵਸਤੂ ਰੱਖੀ ਹੋਈ ਹੈ। ਜਿਸ ਤਰ੍ਹਾਂ ਹੀ ਰਾਕੇਟ ਅਰਥ ਤੋਂ ਦੂਰ ਜਾਂਦਾ ਹੈ ਤਾਂ ਭਾਰ ਤੋਲਣ ਵਾਲੀ ਮਸ਼ੀਨ ਭਾਰ ਵਿੱਚ ਕਮੀ ਦਿਖਾਉਂਦੀ ਹੈ, ਜਾਂ ਦੂਜੇ ਸ਼ਬਦਾਂ ਵਿੱਚ ਐਕਸਲਰੇਸ਼ਨ ਡਿਊ ਟੂ ਗ੍ਰੈਵਿਟੀ ਵਿੱਚ ਕਮੀ ਆਉਂਦੀ ਹੈ। ਇਸ ਨੂੰ g ਡੈਸ਼ ਅਤੇ r ਦਰਮਿਆਨ ਗ੍ਰਾਫ ਵਿੱਚ ਵੀ ਦਿਖਾਇਆ ਜਾ ਸਕਦਾ ਹੈ। ਹੁਣ ਇੱਕ ਬਾਡੀ ਪਹਾੜੀ ਦੇ ਸਿਰੇ ਤੇ ਗਤੀ ਕਰ ਰਹੀ ਹੈ। ਇੱਥੇ h re ਤੋਂ ਬਹੁਤ ਛੋਟਾ ਹੈ। ਗ੍ਰਾਫ ਵਿੱਚ ਤੁਸੀਂ ਵੇਖਦੇ ਹੋ ਕਿ ਘੱਟ ਵਰਟੀਕਲ ਹਾਈਟ ਲਈ ਐਕਸਲਰੇਸ਼ਨ ਡਿਊ ਟੂ ਗ੍ਰੈਵਿਟੀ ਸਰਲ ਰੇਖੀ ਕੱਟਦੀ ਹੈ।
Acceleration due to gravity at a depth. For a point inside the earth, the situation is different. Let us consider the earth to be a homogeneous sphere of radius re and mass me. Hence, the gravitational acceleration at the surface of the earth is small g equal to capital G into me upon re square. If we consider the earth as a sphere of uniform density, then me is equal to the product of earth's density rho and volume of the spherical earth v. Since the volume of the earth sphere is 4 by 3 pi re cube, hence the mass of the earth me would be equal to 4 by 3 pi re cube rho. Hence, small g would be equal to capital G into 4 by 3 pi re cube into rho upon re square, or small g would be equal to 4 by 3 pi capital G into rho into re. Again, consider the earth to be made up of concentric shells as before, and a point mass m situated at a depth small d from the surface of the earth. Here we consider a concentric sphere of radius r, which is re minus d. By using the fact that gravitational force inside a spherical shell is 0, they do not exert any gravitational force on mass m kept at that point. Or we can say that the gravitational force due to the spherical shell above the point is 0. On the other hand, the gravitational force due to the smaller sphere can be calculated by considering it as a point mass. Hence, the net gravitational acceleration at that point is g dash equal to capital G into m upon r square, where m is the mass of the smaller sphere. Since this point is inside the earth, therefore its distance from the center of the earth, that is r, is equal to re minus d. Hence, the relation for small g becomes g dash equal to capital G into m upon the square of re minus d. Here, mass of the smaller sphere, capital M, is equal to the product of Earth's density, rho, and volume of the smaller sphere, that is 4 by 3 pi into cube of re minus d. Substituting the value of capital M in the expression of acceleration due to gravity, we get g dash equal to 4 by 3 pi capital G into rho into re minus d. By dividing the values of g dash and g, we get g dash upon g as equal to re minus d upon re, or g dash is equal to g into re minus d upon re, or g dash is equal to g into 1 minus d by re. This is also a linear equation. We should note that unlike earlier case of a point above the surface, this expression does not have any approximation. Here, the acceleration due to gravity again decreases linearly with the distance as we go down towards the center of the earth. In this case, small g decreases with the slope of minus 1 by re. On the other hand, acceleration due to gravity increases linearly with distance as we move from the center of the earth towards the surface. Let us see what would happen to an object of unit mass when we drop it in the tunnel passing through the center of the earth.
ਜਦੋਂ ਅਸੀਂ ਅਰਥ ਦੇ ਸੈਂਟਰ ਵੱਲ ਗਤੀ ਕਰਦੇ ਹਾਂ ਤਾਂ ਐਕਸਲਰੇਸ਼ਨ ਡਿਊ ਟੂ ਗ੍ਰੈਵਿਟੀ ਵਿੱਚ ਸਰਲ ਰੇਖੀ ਕਮੀ ਹੁੰਦੀ ਹੈ ਅਤੇ ਧਰਤੀ ਦੇ ਕੇਂਦਰ ਤੇ d ਬਰਾਬਰ ਹੁੰਦਾ ਹੈ re, ਐਕਸਲਰੇਸ਼ਨ ਡਿਊ ਟੂ ਗ੍ਰੈਵਿਟੀ g ਡੈਸ਼ 0 ਹੋ ਜਾਂਦੀ ਹੈ। ਪਰ ਅਰਥ ਦੇ ਸੈਂਟਰ ਦੇ ਬਾਡੀ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਸਭ ਤੋਂ ਵੱਧ ਹੁੰਦੀ ਹੈ ਅਤੇ ਇਸ ਦੇ ਕਾਰਨ ਇਹ ਅੱਗੇ ਵੱਲ ਗਤੀ ਕਰਦੀ ਹੈ। ਦੂਜੇ ਪਾਸੇ ਐਕਸਲਰੇਸ਼ਨ ਡਿਊ ਟੂ ਗ੍ਰੈਵਿਟੀ ਵਿੱਚ ਸਰਲ ਰੇਖੀ ਵਾਧਾ ਹੁੰਦਾ ਹੈ। ਜੇ ਅਸੀਂ ਅਰਥ ਦੇ ਸੈਂਟਰ ਤੋਂ ਕਿਨਾਰੇ ਵੱਲ ਗਤੀ ਕਰੀਏ ਤਾਂ ਬਾਡੀ ਦਾ ਵੇਗ ਘਟ ਜਾਂਦਾ ਹੈ ਅਤੇ ਬਾਡੀ ਧਰਤੀ ਦੇ ਦੂਜੇ ਅੰਤ ਤੇ ਜਾ ਕੇ ਵਾਪਸ ਆ ਜਾਵੇਗੀ। ਇਸ ਤਰੀਕੇ ਨਾਲ ਵਸਤੂ ਨਾਰਥ ਪੋਲ ਤੋਂ ਸਾਊਥ ਪੋਲ ਵੱਲ ਸਿੰਪਲ ਹਾਰਮੋਨਿਕ ਮੋਸ਼ਨ ਦਿਖਾਉਂਦੀ ਹੈ।
Let us see the effect of rotation of Earth. Earth rotates once about its axis of rotation in one day and moves around the Sun in 365 days. Since the Earth and any object on the Earth both move together with a constant speed around the Sun, there is no effect in the measured acceleration due to gravity because of the Earth's translational motion. The curved path around the Sun can be approximated to be linear for distances under consideration. Hence, Earth can serve as an inertial frame of reference for the application of Newton's law of motion, irrespective of its translational motion. However, consideration of the rotation of Earth about its axis changes the nature of Earth's reference. It is no more an inertial frame. A particle at a point P is rotating about the axis of rotation. Clearly, there should be a necessary centripetal force required for its circular motion. It is a well-known fact that here gravitational force acts as the centripetal force. To limit our consideration specifically to the effect of rotation, we will ignore other factors that affect gravitational acceleration and consider the Earth as a solid uniform sphere. As we have studied earlier, we can apply Newton's law in a non-inertial reference by providing for pseudo-force.
Pseudo-force is applied in the direction opposite to the direction of acceleration of the frame of reference, which is centripetal force in this case. The magnitude of pseudo-force is equal to the product of mass of the object m and centripetal acceleration. Thus, Fp is equal to mr omega square. Where r is the radius of circular path of the object, omega is the angular velocity of the Earth, and r omega square is the angular acceleration.
After considering the pseudo-force, forces acting on the object at point P at a latitude lambda are pseudo-force, normal force and the gravitational force. The particle is subjected to a normal force against the net force on the particle or the measured weight mg dash. These two forces are equal in magnitude but opposite in direction. That means N is equal to W. It should be noted here that gravitational force and normal force are different quantities. The measured weight of the particle is equal to the product of mass and the measured acceleration. It is given by the expression mg dash. On the other hand, gravitational force is given by the Newton's law of gravitation, which considers the Earth at rest, and the gravitational force F is equal to capital G times the product of the mass of the Earth and mass of the object upon the square of the distance between them, which is equal to mg. Since object is stationary on the surface of the Earth, therefore, all three forces acting on the object should be in equilibrium. Hence, we can say that the resultant of pseudo and gravitational forces is equal and opposite to the normal force. That is, magnitude of N is equal to the magnitudes of F plus Fp.
In other words, resultant of gravitational and pseudo force is equal to the magnitude of measured weight of the object. Since it is an addition of vectors, hence on applying parallelogram theorem for vector addition of gravitational and pseudo forces, the resultant of the two forces is equal to apparent weight or the measured weight.
Hence, the square of mg dash is equal to square of mg plus square of mr omega square plus twice of mg into mr omega square into cosine of 2 pi minus lambda. Since cosine lambda is equal to r by capital Re and cosine of 2 pi minus lambda is equal to minus cosine lambda. On substituting the values of r and cosine of 2 pi minus lambda, we get square of g dash is equal to square of g plus Re square into omega raised to the power 4 into cosine square lambda minus twice of g into Re into omega square into cosine square lambda. Angular velocity of the earth is a very small value, which is equal to 7.28 into 10 raised to the power minus 5 radian per second. The fourth power of angular speed is negligibly small. Therefore, we can neglect the term Re square into omega raised to the power 4 into cosine square lambda. Hence, the expression for the measured weight of the object reduces to square of g dash, which is equal to square of g minus twice of g into Re into omega square into cosine square lambda. Hence, g dash is equal to g into square root of 1 minus twice of Re into omega square upon g into cosine square lambda. It is a binomial expansion. Hence, g dash is equal to g into 1 minus Re into omega square upon g into cosine square lambda plus higher powers of omega. Neglecting the higher powers of angular velocity and considering only the first term of the binomial expansion, we get g dash as equal to g minus Re into omega square into cosine square lambda. This expression shows the effect of rotation on acceleration due to gravity. It is important to notice that only the magnitude is affected by rotation, but its direction is also affected, as it is no more directed towards the center of Earth. Here, Re into omega square into cosine square lambda is known as the reduction in acceleration due to gravity. Let us reanalyze it. There is no effect of rotation at the pole. Being a point, there is no circular motion involved at pole. Hence, there is no reduction in the value of gravitational acceleration there. It can also be obtained from the expression as latitude angle lambda is equal to 90 degree for the pole and the corresponding cosine value is 0. Hence, g dash is equal to g. Whereas, the reduction in acceleration due to gravity is maximum at the equator, where latitude angle is 0 degree and the corresponding cosine value is maximum, that is 1. Hence, g dash is equal to g minus Re omega square. Let us consider the radius of the earth Re as equal to 6400 kilometer or 6.4 into 10 raised to the power 6 meter. Then calculate the reduction in the value of acceleration due to gravity at equator. At equator, the reduction in the value of acceleration due to gravity is Re into omega square, which is equal to 6.4 into 10 raised to the power 6 into the square of 7.27 into 10 raised to the power minus 5. That gives 0.0339 meter per second square. This is the maximum reduction possible due to rotation. Indeed, we can neglect this variation for all practical purposes except where very high accuracy is required. ਵਿਦਿਆਰਥੀਓ, ਹੁਣ ਅਸੀਂ ਅੱਜ ਦੇ ਪਾਠ ਦੇ ਅਖੀਰ ਤੇ ਪਹੁੰਚ ਗਏ ਹਾਂ। ਹੁਣ ਮੈਂ ਜਲਦੀ ਨਾਲ ਕੁਝ ਪ੍ਰਸ਼ਨ ਪੁੱਛ ਕੇ ਇਹ ਪਤਾ ਕਰਦੀ ਹਾਂ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਵਿੱਚੋਂ ਕੀ ਸਿੱਖਿਆ ਹੈ। ਮੇਰਾ ਪਹਿਲਾ ਸਵਾਲ ਹੈ, what is the value of acceleration due to gravity at a latitudinal angle lambda? The answer is, at a latitudinal angle lambda, value of acceleration due to gravity is equal to small g minus re into omega square into cosine square lambda. अगला सवाल देखो, what assumptions are to be taken for finding the expression for gravitational acceleration? The answer is, the earth is assumed as uniform spherical and stationary body. ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਦਾ ਪੂਰਾ ਲਾਭ ਉਠਾਇਆ ਹੋਵੇਗਾ। ਪਾਠ ਨੂੰ ਧਿਆਨ ਨਾਲ ਸਮਝਣ ਅਤੇ ਸੁਣਨ ਲਈ ਸ਼ੁਕਰੀਆ। ਅਗਲੀ ਵਾਰ ਇੱਕ ਹੋਰ ਨਵੇਂ ਵਿਸ਼ੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ। ਹੁਣ ਇਜਾਜ਼ਤ।